So today we're going to look at section 3.4, and it's really going to be on two different things. One of them is the rational root theorem, and the other one is synthetic division. So in that last problem we looked at, okay, we had an answer of, well, I got rid of it, but it was that negative 0.002. And it was a number that didn't look like it was going to be a fraction. Well, if you have a graph and it crosses the x-axis, sometimes it can cross the x-axis in a spot that's a fraction. Like if you got 0.75, that's a fraction, 3/4. Sometimes it crosses the x-axis in a number that's not a fraction. What we're going to focus on for most of today is looking to find a place that crosses the x-axis that is a fraction. So I'm going to show you a set of steps you can do to figure out if a graph crosses the x-axis at a fraction. Okay. And then the second thing we'll talk a little bit about is synthetic division, which is a quicker way to do long division. And it can work for more than what I'm going to show you. But I'm only going to show it to you for one specific thing. So how do you figure out if a graph crosses the x-axis at a place that's a fraction? You use this theorem. What this theorem does is it generates a list. It doesn't give you an exact answer. It gives you a list of possible options of where the graph could cross the x-axis. It's still up to you to check that list, but at least it gives you a list, so it gives you kind of a starting point to work with, and then we can go from there. So when we do a problem, we're going to have a polynomial. That's what that represents. It's going to start with the highest exponent, then it's going to drop down to the next lowest exponent, next lowest, till we get to the x, and then we'll end with a constant. So when we do a problem, it's going to look like this. You'll have an exponent, then it'll drop down, till you get all the way down to the constant. Okay, so that f of x, it's the same thing as this. It's just I don't have any numbers filled in. Okay, a couple things that are important here. All of these things I'm circling in red have to be rational. So in other words, you can't have couldn't do something like this. You couldn't have the number in front of x to the 5th be square root of 10. This theorem wouldn't work. The numbers in front have to be nice numbers that could be written as fractions, like 10, -3, and 1. The other thing that's important is, I'll underline them, the coefficient of the first term and the constant at the end cannot be a 0. So I'd never give you a problem where they are zeros if I want you to use this theorem. And the two most important things are what I just highlighted in green. Those are the two numbers that we're going to have to look at when we want to do this theorem. So in this problem, it would be the 10 and the 6. Those are the two numbers we'd be focusing on. So if you're going to cross the graph at a place that's a fraction has a numerator and a denominator. I'm representing the numerator as p and the denominator as q. So how do you figure out that fraction? Well, p comes from something. So p comes from something in the problem, and the q comes from something else. Has to do with the two things that are highlighted in green. P is a factor of the constant. So whatever number is at the end, let's say the number at the end was a 6. The factors of 6 are 1, 2, 3, and 6. So does that mean there's more than one option for P? Yes. There are many options for P. Like I said, this theorem is going to generate a list of possibilities. We're still going to have to check them out using the calculator.
What's P stand for?
P represents all the factors of the constant term. It doesn't have a name, they just use the letter P. And Q represents all the factors of the number in front. Okay, that's the leading coefficient. So let's say the leading coefficient was a 10. Okay, your factors of 10 are 1, 2, 5, 10. And all the negatives. -1, -2, -5, -10. Now, this is going to generate, and we're going to do this in the next problem, it's going to generate a list. I'm not saying every single number in the list is a place where it crosses the x-axis. This list that we're going to make, it's a list of possibilities. It's possible that we go through all this work, we make the list, and none of them work. If that was the case, then that means this graph never crosses the x-axis at a place that's a fraction. It might only cross the x-axis at a place that isn't a fraction. But we won't know that until we try the theorem. Okay, so important thing, P are all the factors of the number at the end. Q are all the factors of the number that are in front. Right, let's try it on this example. And I'm just going to add in the word possible. List all possible rational zeros. Okay? In other words, I want to know every possible place that this graph could cross the x-axis at a fraction. So the first step is to list all the values for P and all the values for Q. Let's go back up. So P are the factors of the constant. What's the constant in this problem? Yep.
-6.
-6. What are all the numbers that divide into -6?
1, 6, 2, 3, and all those with negative.
Yep. 1, 2, 3, and 6. And then all the negatives. So if this graph is going to cross the x-axis at a fraction, the numerator of that answer has to be one of those numbers. The denominator would have to be a factor of the leading coefficient. What's the leading coefficient? Yep.
10.
10. And what are all the numbers that go into 10?
1, 2, 5, and then all those with negative.
Yep. 1, 2, 5, and 10.
No, you don't want to do that.
So now, if it crosses the x-axis at a fraction, the denominator is going to be one of those numbers. Now we have to list all the possible p's over q's. So the way I do it is let's start with that one in the top, and then list all the different denominators you could have with a 1 in the top. So here's our list. We could have a 1 in the top over a 1 in the bottom. We could have a 1 in the top, and we could have a 2 in the bottom. We could have a 1 in the top, we could have a 5 in the bottom. And the last one, we could have a 1 in the top and a 10 in the bottom. And the negatives of all those as well. So those are 4 possible places that it could cross the x-axis at a fraction. Okay. Now let's do the ones with a 2 in the top. Okay. I could have a 2, and my first denominator would be a 1. I could have a 2, and my next denominator would be 2, but 2 over 2 is what number?
1.
We already have that one, so that's a repeat. So we don't have to write 2 over 2, because that's 1. Next one would be 2 over 5. Don't have that. And the next one would be 2 over 10, but 2 over 10 is 1/5. So that's another repeat. So that's all the ones with a 2 in the top. Right, now let's do 3. Okay. First one would be 3 over 1, then 3 over 2, and then 3 over 5. And the last one, 3 over 10. We didn't have any of those. This one has more possibilities than a typical problem, but I'm just trying to get you to understand like how to list them all out. Okay, in general, we won't have this many to list. Right, and now let's practice doing it with a 6 in the top. Okay, so the first one would be 6 over 1. We don't have it. The next one would be 6 over.
We have that.
We have that because what is 6 over 2?
3.
3. We already have 6 over 2. The next one would be 6 over 5. And the last one would be 6 over 10. But that's 3 over 5. Okay, so that's our list. So if this graph is going to cross the x-axis at a fraction, it would have to be one of the numbers in that list. Is it one of the numbers in that list? I don't know. We'd have to actually graph it and see. But if it is going to cross at a fraction, I guarantee it's one of those numbers. And the biggest number in this list is a 6. The smallest one is a -6. So what we have now is a pretty small section on the calculator to check. We don't have to check at like 200 because 200 is not an option in this list. 6 is the biggest. So that's as far as you need to check. And that's what we'll do next. We're going to check it on the calculator. All right, so let's type that in. We can do a standard window because -10 to 10 will cover every number that's in this list. You could even do -6 to 6 if you want to zoom in a little bit. So 10x to the 5th minus 3x squared plus x minus 6. Okay, so there's our graph. Now let's bring that over here, make it a little bigger. What I want to do now is narrow down that list. Based on the graph, a lot of these numbers don't even seem close to that. Which number or numbers in that list seems like it's pretty close to where it crosses? 2? Well, 2 would be right there. So I don't really think it doesn't look like it's that close to 2. At least to me. I'd say it looks like it's pretty close to 1, or 1 over 1. So narrowing this list down, I'm going to write possible, we'll call these like candidates for the root. So these are when we narrow the list down a little bit. I definitely would say +1. I wouldn't say -1. Is there any other number that it looks like it could be close to?
6 over 5.
Yeah, 6 over 5. That's just a little bigger than 1. That's like 1.2. We've seen when we zoom in, sometimes we don't know exactly what's happening. So I would say it could be 6 over 5. I'd be leaning more towards 1, if anything. But I don't think any other number in this list even makes sense. 0.3, 0.6, 1.5, 3, 0.4, 0.1. It's not really close to any of those. So these are the possible candidates once we eliminate the ones that don't make sense. Any question on how we got those two? All right. So now, let's actually find what it is. Second calc, 0. Pick a point left, right, and then do your guess. And the root comes out to 0.9505. Okay, so just make sure I remember what we did. This is a list of possible rational zeros. Is 0.9505, which is the real answer, in that list?
No.
No. So what do you think it means about this number then?
Irrational.
It's irrational. Exactly. So in this problem, let's write that down. The actual root is about 0.9505. There is no number in this list that's 0.9505. None of them. That's the list of rational possibilities. Because that number isn't in the rational list, it must be an irrational root. So unfortunately, rational root theorem didn't really help us in this problem. That can happen.
Why wouldn't we just say it is, why wouldn't we round it to 1? I thought the calculator wasn't always exactly correct.
Well, it's correct up to that many decimal places.
Oh, okay.
So when I write 0.9505, that's not the exact answer. Even if I wrote 0.95054589, that's still not exact. But it's accurate up to where it's telling you. So it's not 1. It looked like it was 1, but it wasn't. So the actual root is 0.9505. This is not in the list of rational roots. So it must be irrational. The hope is that when you do the rational root theorem, you actually find a number that's in that list. That's what we usually want to happen. But this time it didn't. So if I asked you on the test, what are the rational roots to this problem? What would you say? Yeah?
None.
None. There are none. And then if I said why, you'd say, well, I used the calculator, I found the root, and it didn't match any numbers that were in my list. So it has to be irrational. Again, we're going to hope this doesn't happen most of the time. Okay, this time it did. Any questions on that? So we really just did 2 examples. The next one was to show that the root was irrational and use a graphing calculator. We just did that. That was example 2. Let's try one more. I don't want to go through the whole thing, just listing the P's and Q's. Let's say we had 3x squared plus 2x plus 4. What are the possible answers for P in this one? What are the factors of the constant? Yep.
1, 2, 4, and it's negatives.
Yep. So not as many as last time. 1, 2, 4. And then let's list the Q. Okay. What are your possible answers, possible factors for Q? Yep.
1 and 3 is the right number.
Yep. That's more typical of the P's and Q's. That's a lot less than the last one.
Yeah.
So now, to make your list, what would be your possibilities in the list this time? 1 over 1. Yep. Let's do all the ones that have 1 first.
1 over 1, 1 over 3.
1 over 1, 1 over 3. Yep. 2 over 1, 2 over 3. 4 over 1, and 4 over 3. So now we got a much smaller list. If this graph crosses the x-axis at a place that's a fraction, it's going to be a number in that list. And I just made this one up, so I don't know if it does or not. But I just wanted to practice the P's and Q's one more time. Any questions on how to make that list? All right. So now we're going to combine making that list with something called synthetic division. So synthetic division gives you a quicker way to do long division. As I said, you can use it in more cases than I'm teaching you. The case I'm going to teach you how to use it for is when you have x minus a number in the denominator. If you don't have x minus a number in the denominator, you have two options. You can learn on your own how to use synthetic division in other cases, or you can go back to what I taught you yesterday with long division. Okay, so let me, I'm going to do it like I did yesterday. I'll just go like this. Let's divide. Actually, I need the problem. I'm just going to reword this a little differently. Divide 2x cubed minus 5x squared plus x. Was there a number on the end? Yeah, there was a plus 3. I don't know what happened to that. Plus 3 divided by, that's right there, x minus 3x. Okay, so that's the problem we're going to do. And we'll do that as I show you the steps. Okay, so the first thing is, are we dividing by something that's of the form x minus a number? Yes, we are. So step 1 is take the number that comes after the minus sign, put it on the outside of a bracket, and then on the inside, fill in all the coefficients of the numerator. Make sure you put in a 0 if you're missing anything. So what would be my coefficients I would write down? Yep, Gary.
2, -5, 1, 3.
Yeah, we're not missing any. 2, -5, 1, 3. Perfect. And then draw a line. Okay, the next step. Bring down the first coefficient. Put it below the line. That's the first step. Okay, the next step. Multiply the number on the outside by the number you just brought down. What's 3 over 2 times 2?
3 over 2 times 2?
Hmm? 3. 3 divided by 2 times 2 gives you 3. And you're going to write that answer right there. So you multiply the number on the outside by the number you bring down and put the answer in the next column. And this is what's different from long division. Add. You don't subtract. Subtraction is with long division. What's -5 plus 3? -2. And now you keep doing that. Okay, so now we repeat it until we're done. And then I'll tell you what the answer is. Okay, so now what's -2 times 3 over 2? -3. And then add that column with -2. And what's -2 times 3 over 2? It's -3. And then add that column. 0. Anyone have a guess what the 0 is? That's my remaining. Which means this part is my quotient. So the last row contains the coefficients of the quotient and the remainder. So if you're going to write down the quotient, it would be constant, linear, squared. So it's a 2x squared minus 2x minus 2. That's your quotient. And the remainder is 0. And that's how you do synthetic division. Now, a couple things happened here. Since I got a remainder of 0, what does that mean about this?
That's a factor.
That's a factor. If you were trying to factor this numerator, that is one of the factors you would want to use. Go. Now, if this is a factor, then what is that? The 3/2. That's a 0. It's also called a root, and it's also the what? It's also the x-intercept. Yep. So 3/2 is a root, or a 0, or an x-intercept. X minus 3/2 is one of the factors. What's the other factor? This is kind of like yesterday when I said 12. I want you to factor the number 12, and 3 is a factor of 12. How did we get the other factor?
We divided it.
We divided it out.
Just the 2x squared.
Yes.
2x squared.
Exactly. That's the other factor. It's when you divide something by, well, when you divide something by a factor, the answer you get is the other factor. That's the other factor right there. Now, what if this remainder came out to like 1? Then x minus 3/2 would not have been a factor. Okay. But it came out to 0, so it was. Okay. Does everyone have the 4 steps for synthetic division?
Did you go down on the right one?
Yeah, it keeps going back up on me. Yeah.
How did you get the x's for the quotient?
Well, the first one is your constant. The next one is your x, and the next one is your x squared.
Oh,
And then if you had another one, that would be the x cubed.
okay.
And another one would be the x to the 4th. So,
We just go down.
yeah. So these are the numbers you just put right in front of the x's. Okay, let's try another synthetic division. Yeah.
I have one question. For that one, for example, 3, how did you get like the 3, -3, like the -3 and -3, like under the first step?
So these are all the results of multiplications.
Okay.
2 times, think of 3/2 as 1.5.
Okay.
If you take 1.5 and double it, you get 3.
Okay.
And then when you add those, you get -2. And then 1.5 times -2 is -3. We're gonna do another one, but we're not gonna have a fraction. I think this one will be a little easier. When you see SD, that means synthetic division. Okay, use synthetic division. The book refers to it as Horner's algorithm. I think that might be the person that figured this out. So if you see Horner's algorithm in the homework, just think in your head, okay, he said use synthetic division. It's the same. All right. Are we dividing by something that looks exactly like it's supposed to?
No.
No. It's supposed to be x minus, and then something in that box. -3. Whatever's in that box, that's what goes on the outside when you do synthetic division. Okay, what would my coefficients be this time?
3, 7, 0.
0.
1, and then 11.
Yep. You got to put a 0 because you're missing the x squared term. Okay. What do we do with the 3?
Down.
Just bring it down. And then -3 times 3. -9. And what do we do with this column? Add it up. What's 7 plus -9? -2. What's -3 times -2? 6. Add it up. 6. What's 6 times -3?
-18.
Okay, add it up.
-17.
Now we have -17 times -3.
Just positive 51.
Positive 51. And then add it up.
40.
40. Excellent. Now let's write quotient and remainder. Well, what's my remainder? Okay, so remainder is 40. What is my quotient?
3 cubed minus 2 squared. 3x cubed minus 2x squared plus 6x minus 17.
That's your quotient and remainder. So what do we know about x plus 3?
It's not a factor.
It is not a factor of 3x to the fourth and all that stuff. X plus 3 is not a factor, which means negative 3 is not a
0.
It's not a 0. It's also not a root. It's not an x-intercept. Any questions on that one? All right, let's try this one. It's kind of the same idea. I want to show that 3 is not a 0. So what does that mean I would want to show is not a factor? Showing 3 is not a 0 is the same as showing...
X minus 3.
Right. So what I'm basically going to do is this problem. I'm going to divide that by x minus 3 using synthetic division. And to show that it's not a 0, I'm going to hope that what happens? The remainder doesn't equal 0. Yeah. So take the number after the minus sign. And now we're basically going to do this division problem out. 2, 5, negative 2, negative. We're not missing anything. Bring down the 2. 3 times 2.
6.
5 plus 6. 3 times 11.
33.
Plus negative 2.
31.
31 times 3.
93.
93. Plus negative 3.
90.
90. So what's my remainder? Yeah. So when I tried to divide by x minus 3, I got a remainder of 90. That means x minus 3 is not a factor, which means 3 is not a 0. 3 is not a root. 3 is not an x-intercept. That's how you show it. Any question on that one? Now, I gave you that number to try. You're going to have to figure out the number to try on your own now. And the way we figure it out is we need a list of possible options. How do we get a list of possible options? The rational root theorem. That will give us a list. Now, we don't just want to sit here and start trying every number in the list. Even if you only had 6 numbers in the list. That's still a lot of numbers to do synthetic division with until you find one that gives you 0. Because that's the goal. We want to find one that gives us a remainder of 0. So we'll make the list, and then we'll narrow the list down. That's where I wrote the possible candidates. So we'll narrow it down, and then once we think we have one that works, we'll use synthetic division, just like we did in the last problem. So rational root theorem, graphing calculator, synthetic division. That's what those stand for. Yeah.
If we're putting in a graph calculator anyways, why do we need synthetic division? Why can't we just find the 0 with the calculator?
Because the calculator can only find a certain type of zeros. The calculator can only find real. So tomorrow, when we do imaginary ones, if you don't do synthetic division, you won't have something to plug into the quadratic formula because it won't be a quadratic, it'll be a cubic. And notice, each time you start with something, you started with a cubic and you ended up with a quadratic. Same thing here. You started with a 4th degree, and when you wrote your quotient, it was a 3rd degree. So every time you use synthetic division, that exponent drops down 1. And in order to really be able to work with it, we'd have to take it all the way down to a 2, because we have the quadratic formula. So that's what synthetic division does. It takes this exponent, and it drops it down 1 number every time you do it. So let's try it. Okay, let's fix this. All right, so this one's not as bad because it's a cubic. We can't work with it directly in quadratic formula because this would have to be a 2. But if we can do synthetic division one time, it'll take it down to a 2. And then we can use quadratic. All right. So let's make a list of possible options and see where we're at. What are all the factors of the constant this time? Plus or minus 1 and plus or minus 2. Now Q are all the factors of the leading coefficient. It's a 1. It'd just be 1. So Q doesn't make a difference in this problem. When you put this over Q and then that over Q, putting it over 1 doesn't change it. So what would be all the numbers in my list? It's basically just P in this case. We don't even need the Q. So what that tells me is on the calculator, a standard window is more than enough to be able to see if it crosses the x-axis between -2 and 2. That's what I'm going to check. Okay, so now we got to put it in. I don't want to waste time doing synthetic division there's only 4 things to try. 1, -1, 2, -2. But I don't want to waste time doing it until I know I have the right one. And that's what the calculator helps me find. So x cubed minus 3x minus 2. Okay. Where does it look like it crosses the x-axis?
-1 and 2.
I would say -1 and 2. If you think it's both, you could try either one. The quick way to check it is go to the table, and let's try 2. Actually, it's already typed in. If you plug in 2, you will get 0. So we know 2 is going to be an answer. So that's the number that I'm going to choose to divide through by synthetically. 2.
When on the table, how do you input which number you're looking for?
You have to set it up first when you go to second window, and then you have to put your independent variable on ask. Okay, so we're going to try 2 because we checked it, we know it's going to work. And then what would be the numbers on the inside?
1, 0, -3, -2.
-2. Okay, we already know we're going to get a 0 for the remaining. If we don't, we did something wrong with the synthetic division. Bring down the 1. What's 2 times 1?
2.
And then 0 plus 2.
2.
2 times 2?
4.
Plus -3?
1.
1. And what's 2 times 1?
2.
And -2 plus 2?
0.
There we go. So now we can start making a list of rational zeros. Okay, so we've got 2. That's definitely 1. Now, we focus on the quotient. If I write that out, what's my quotient? Yeah, 1x squared, or you can just put x squared. Now that you've pulled one of the zeros out using synthetic division, take what you have left and find the rest of the zeros. And that's the rest of it. So that, sometimes you need to use quadratic formula. In this case, you can factor it.
How come when doing synthetic division, why did we use 2 like that?
Because 2 was one of the roots on the graphing calculator when we did that.
So you could use 1.
You could have used, I think it was -1.
Or -1.
You could have done -1. It wouldn't have mattered.
Alright.
Both of them would have worked. Now, how does this factor?
X plus 1 plus x plus 1. Or not plus 1, x plus 1.
So x plus 1, x plus 1. Yep, that's how it factors. And what would you plug in here to get 0?
-1.
And then what would you plug in here?
-1.
So -1 is a repeated answer. A lot of times when you see a graph go up, touch the axis and bounce away, you're going to get that answer repeated twice. when we write the roots, you don't have to write this answer twice. All you have to write is this. 2 and -1 are the zeros. -1 is repeated twice, but that you don't have to tell me. Okay. Any question on that one? All right, let's do the last one. Let's try this one. That's this one. Okay, so find all real zeros. And then when you find them, tell me if they're rational or irrational. Okay, let's start. If it's a quadratic, we can just go right to quadratic formula and be done. Is it a quadratic? No. So then we're going to have to find a rational root, divide through by it synthetically, and then take that and put it in the quadratic formula. If you can't find a rational root, then you're stuck. You're not going to be able to do this problem without a calculator. Because factor by grouping is not going to work either. There's nothing you can factor out of x plus 2. So we have to find a rational root. Okay, what are my possible values for p in this case?
Positive, -1. Positive, -2.
Okay. And my possible values for q?
Positive, -1. Positive, -2.
Positive, -3. So now when I make my list, what are my possible values when I do p divided by q?
1, 2,
So what is it? 1 over 1 over 1, yeah. 1 over 3. 2 over 1, 2 over 3. Okay, so if it's going to cross at a fraction, it has to be one of those 4, well, technically 8 numbers. Right, let's put it in and see where it crosses. So it's 3x cubed minus 8x squared plus x plus 2. Okay, out of those 8 numbers, which ones seem like they could be right? All right, it could be 2 over 3. We can check it on the table. Second table. Let's type in 2 over 3. 2 over 3 is correct. And is there any other one that seems like it could have been right?
-1 over 3.
It looks like it could have been -1 over 3, but it's not. So -1 over 3 is, we don't want to waste time doing that one because it wouldn't work. So we want to do 2 over 3. Well, let's do it. 2/3. And what numbers go on the inside?
3, 8, 1, 2.
Negative 8.
All right, negative.
So 3, -8, 1, and 2. Okay, bring down the 3. What's 2 divided by 3 times 3?
2.
2. -8 plus 2?
-6.
-6. Now, if you have trouble with the fractions, it's 2/3. You just put times -6 in the top. What's 2 times -6?
-12.
Divided by 3.
-4.
-4. What's 1 and -4?
4. -3.
-3. And now 2 divided by 3 times -3. -2. And my remainder? 0. So now when we're making our roots, 2/3 is one of them. And what's going to be the polynomial I look at now to get the other ones?
3, 6, 3, -6.
And what would that be if you put it in a polynomial?
3x squared -6
Minus 3. Now, what kind of polynomial is that? It's a quadratic. A, B, C. We're going to use quadratic formula and be done with it. So we've got -b plus or minus the square root of what comes next.
B minus 4ac. -b minus 4ac.
B squared minus 4
AC.
AC divided by
2A.
2a. So you're going to be subtracting a negative, so that's going to turn positive. What's 4 times 3? 12 times 3. So it's 36 plus 36. 72. So the other roots are 6 plus or minus square root 72 over 6. You can reduce square root 72. I'm not worried about that. That's how you get the other two roots. And if they came out imaginary, that would be the only way to get the other two roots. They didn't, and they won't in tonight's homework. Okay, so that's the rational root theorem and synthetic division. Okay, so that's the homework for tonight. So it's 11 questions on page 183. It's 1, 2, 5, 6, 9, 10, 13, 14, 17, 18, and 27. We'll go over that first thing tomorrow. We'll finish all the material for this week on 3.5, and then our test will be on Thursday.
You're up to many. I gotta give someone else a chance.